Okay, topic 6, collision theory, rates of reaction. The greater the probability that molecules will collide with sufficient energy and proper orientation, the higher the rate of reaction. So we look at some of the things that affect these rates of reaction and how to measure rates of reaction. So this is what we need to be familiar with by the end. Just obviously for two particles to react, we need them to collide. Right? And there's got to be this certain minimum energy in that collision. That's referred to as the activation energy. The other thing to consider is that they must also have the correct orientation, and we've got to hit in the right place. So if something like this molecule here that will react with, let's say, bromine, to test for an alkene group, it's reacting with this piece. If the bromine hits there, there's not going to be a reaction. Okay, it's got to be hitting here. And this orientation, getting the right part of the molecule, is particularly important in things like enzymatic processes where we know they have a very specific active site and our substrate has to go into the active site correctly. So one factor that can affect the rate of reaction is concentration. As you can see here, going between these two pictures, I've increased the concentration. I've got more particles in this space, and as a result I've got more collisions. More collisions means I'm going to get a faster rate of reaction. And similarly, if I was to take a gas and if I was to increase its pressure, so let's say that my container was that size and then I increase the pressure, I decrease the volume of that container for the gas, then you can see I'm going to be getting more collisions, and as a result I'm going to get a faster rate of reaction. Now, it's worth keeping in mind that if you were to change the volume of a solution, you're not necessarily, well, in fact you won't be changing the rate of the reaction. So if we've got some solid in the bottom, there's our solution and that they're reacting. Let's say I then change my volume to this. So I do have more particles, but I've increased the volume. I've not really done anything down here. I've not changed the concentration down here in any way, and so the rate of reaction isn't going to change. So just be careful with that, that for a solution, if you change its volume, we're not going to see a change in its rate of reaction. It's the concentration that has to change, because then we get more collisions. Surface area, also important. When you cook food, you'll be chopping it up so it cooks a bit quicker. You can see there with this example, taking this cube, cutting it into smaller cubes, you've increased the surface area, there's going to be more collisions, faster rate of reaction. Temperature. Now this is nicely explained by a Maxwell-Boltzmann distribution, and we can see here that the kinetic energy of the particles is also proportional to the temperature in Kelvin, so keep that in mind. That temperature in Kelvin is often referred to as the absolute temperature. Right, so in my sample, let's say T1 is room temperature, in my sample there, some particles have very little energy, some particles have very high energy, most are kind of somewhere in here like this. Now if I was to heat that up, if I heat up that sample, the particles obviously get more energy. I find that I now have more at this end. That curve is shifting across, and the reason we're seeing that drop is because the area under the curve has to stay the same. That area under the curve is representing the total number of particles in my sample. And the total number of particles hasn't changed. I've just now got more up here and less down here, so we see that top drop a little bit. Now in terms of talking in terms of kinetics, if I consider my activation energy to be this amount of energy, hopefully you can see that at a higher temperature, more of my particles now have an energy greater than or equal to the activation energy and are able to react, which gives me a faster rate of reaction. Catalysts, fourth way in which we can alter these reaction kinetics. Catalysts act by providing an alternative pathway for a reaction to occur. They can be heterogeneous in different phase. So iron-Haber process is nitrogen hydrogen gas reacting to form ammonia. It uses iron solid in there. Or it could be homogeneous in the same phase, and enzymes in the body would be an example of that. But what you can see is that my activation energy is lowered by the presence of this catalyst, and you can see that in both these diagrams here. Right, so measuring these rates of reaction, very often units that we're working with are moles per decimeter cube per second, because we're looking for changes in concentration per unit time. And it might be that we measure how quickly a reactant disappears or how quickly a product forms over time. Now, either way, the rate of reaction is going to be fastest at the very start of reaction. You can see here this is it slowing down till eventually there's no more change, it's stopped. It's fastest at the start because that's where we've got our highest concentrations, and we saw that higher concentration gives us faster rate of reaction. So how can we monitor this? You've probably seen some examples in the lab. If you've got a gas being produced, you can very simply just sit it on some scales, and as that gas disappears, you will see the mass decrease. And if every 10 seconds or so, if you take a reading here, you'll be able to get a curve like you saw on the other page. Alternatively, if you didn't like using the scales, you could wire that up to a gas syringe. And again, every so often, if you were to take a reading of the volume of gas in that syringe, again, you could see how quickly that product was being formed. Many reactions will involve a color change. You can use a colorimeter. You can set that up, and you can see how that color gets darker or how it fades away. Again, monitoring it over time will give you an indication of rate. So here's an example of a rates experiment. So over a passage of time, experiment was set up, gas was being produced, so they measured how much gas volume was produced. Have a go at processing that and see if you can work out the initial rate. The initial rate, actually I'll give you help here, you're going to see a graph that looks maybe something like this. Starts off very fast, slows down. We're interested in the initial rate because we know about all the concentrations of stuff there. So to work out that initial rate of reaction, we draw what's called a tangent. Now a tangent is a line which just touches at the point we're interested in. So it's just touching that initial value, and I'm going to work out my gradient of that increase in y over increase in x. That's going to be in centimeters cubed per second, and that's going to be my initial rate. So there we go, you can see that being worked out there for you. Right, that's what we've covered.